Welcome back to Simple Quant. Today we will cover all of conditional probability. Today's video is the third video in a 12-part series covering all of college probability. In this video, we will cover conditional probability, the multiplication rule, Bayes formula or Bayes rule, odds, and we'll conclude with independence. Let's get to it. So to start our discussion of conditional probability, let's say you roll a die. What's the probability you got a 4 given that you rolled an even number? The main word here that implies conditional probability is the word given. If you ever see the word given, it's a conditional probability question. So how can we figure this out? Normally, if we roll a die, we can get any of these 6 options. That's our sample space. That's all the possible outcomes. But in this question specifically, we narrowed down our sample space. The only possible outcomes is that we rolled an even number. That's the given part. So instead of having all 6 of these options as our possible outcomes, we actually only have these 3. So these 3 die are our sample space. These are all the possible outcomes when we roll the die, given that it's even. Now, what's the probability that you got a 4, given that this is our possible outcomes? Well, since we know all these die rolls are equally likely, this 4 will come up 1/3 of the time. Our answer is 1/3. The probability that we got a 4 given that we started with only even numbers is 1 in 3. So that's the answer. Now let's look at another example. So what's the probability you got a 1 or a 3 given that you rolled an odd number? Well, again, our total sample space is all 6 possible die rolls. But in this case, we restrict it to just the odd numbers. That's the given part. So these are the only 3 possible values. Now what's the probability that we got either a 1 or a 3? Well, out of these 3 possible options, 2 of them are 1 or 3. So our final answer is 2/3. In general, the probability of A given B, this symbol right here is a given, the straight bar, equals the probability of A and B divided by the probability of B. So where's the logic behind this formula? Well, if we look back at our problem with the evens or odds, the probability of B is the odd number, and the probability of A and B is the probability that you rolled a 1 or a 3 and got an odd number. Intuitively, it might make sense to just restrict the sample space to B and then figure out what's the probability of getting A with the new sample space. But if you don't know the sample space, this is the formula you use to calculate conditional probability. So let's try a practice problem. So let's say our friend, let's call him Floob. So our friend Floob right here is hanging out with a group of girls, and he likes only a certain number of them, and only a certain number of them like him back. So let's say Floob likes these specific 3 girls, but only these 4 girls like him back. So our question is, what's the probability Floob is liked back given that he likes someone? See if you can figure this out. Okay, let's start with defining our problem. What are the events we care about? Well, the first thing we care about is whether Floob likes the woman or not. So let's call that event A. A equals the event that Floob likes. We also care about whether the woman likes him back or not. So let's call that event B, the event that the girl likes Floob. Now the question that we were asked is the probability that he's liked back given that he likes someone. So that can be written as the probability of B given A. The probability that the girl likes Floob back given that Floob likes the girl. Now from our formula that we saw earlier, this probability is equivalent to probability of B and A over the probability of A. So how can we find this term right here? Well, what's the probability of A? What's the probability that Floob likes a girl? He likes 3 out of the 5 girls. So the probability of A is 3/5. Now what's the probability of B and A? The probability that when Floob likes a girl, the girl likes him back. Well, that would just be these 2 girls right here. That's 2 out of the 5. So that's 2/5. So from there, we know the answer to our question is is 2/5 divided by 3/5, which is the same as 2/3. Now let's try another practice problem. Let's imagine you have a normal deck of cards, 52 cards, 13 of each suit. Now let's say you draw a jack of hearts. The conditional probability question is, what's the probability you drew the jack of hearts given that you drew a heart or a face card? See if you can figure it out. Alright, to start, let's define our events like always. So our first event is that we draw a jack. So let's say A is the event you draw a jack. What's the probability of A? Well, the probability of A is just the probability you draw any card from a deck of 52. So that's 1/52. Now the other event we want to know is, what's the probability you draw a heart or a face card? So let's call that B. Draw a heart or face card. So how many ways are there to draw a heart or a face card out of a deck of 52? Well, the number of hearts is 13. If you go from ace as 1 all the way to the king as 13, that's 13 possibilities. And then how many ways are there to draw a face card? Well, there are jack, queen, and king for every suit. So that's 12 total face cards. Now we overcounted a little bit because we counted both the jack of hearts, queen of hearts, and king of hearts twice. So since we overcounted, we subtract those 3 double counted cards, and the total number of ways to draw a heart or a face card out of a deck of 52 is 22. So what's the probability of B? The probability of B is 22/52. So again, what we're looking for is the probability you drew a jack given you drew a heart or a face card. So that can be written as the probability of A given B. And using our equation, that's the same as the probability of A and B over the probability of B. So we're looking for this right here. So the probability of A and B is looking for the probability you both draw a jack and you draw a heart or a face card. But we know that if you draw a jack of hearts, that is also a heart and a face card. So the top term is also the same as the probability of A in this case. So we're just looking for the probability of A divided by the probability of B. And using what we calculated before, that's the same as 1/52 divided by 22/52, which gives us a final answer of 1/22. Next up, we have the multiplication rule. So what is the multiplication rule? The multiplication rule states that the intersection of n events is the same as the probability of the first event times the probability of the second event given the first event, and so on till you get to the probability of the nth event given that all the previous events also happened. Now this might be a little confusing, but let's think of a basic example real quick. So let's say event 1 is that you're tall. And let's say event 2 is that you're smart. The multiplication rule basically says that the probability that you're tall and smart is the same probability as you first figuring out the probability that you're tall and then multiplying the probability that you're smart given that you're tall. So it's like splitting up the and into a bunch of different sections. So you start with, are you tall or not? And then, if you're tall, are you also smart? So if you multiply the probability that you're tall times the probability that you're also smart, if you're tall, that gives the probability that you're smart and tall. So let's try a few quick practice problems. What's the probability you draw 2 aces when drawing twice from a deck with no replacement? So let's define our 2 events. Let's say A is you draw an ace on first draw. And let's say B is an ace on second draw. Based on the multiplication rule, what we're looking for, the probability of A and B, the probability you draw an ace on the first draw and then an ace on the second draw, equals the probability of drawing the ace first, and then multiplying that by the probability that you draw an ace on the second draw, given that you already drew the ace on the first draw. So how can we find this term right here? Well, what's the probability of drawing an ace on the first draw? There are 4 possible aces and there's 52 possible options, so that gives us 4 out of 52. The probability of A equals 4 out of 52. Now what's the probability of B given A? So what's the probability we draw a second ace given that we already drew the first ace? Well, there are only 3 aces left in the deck after we drew the first one, and there's only 51 options left because we already drew one of the cards. So the probability of B given A is 3 divided by 51. So now plugging in what we know in this equation, we get the probability of A and B equals 4 divided by 52 times 3 divided by 51, and that will be our solution. So now for a quick addition to that problem, what's the probability you now draw 3 aces when drawing 3 times from the deck with no replacement? If we define our events similarly to how we did previously, the probability we're looking for, the probability of A, B, C, you get an ace on the first, second, and third draw. Using the multiplication rule, is the probability of A times the probability of B given A times the probability of C given A and B. From the previous problem, we already know this part of the equation equals 4 out of 52 times 3 out of 51. Now the only thing we have to figure out is what this term equals right here, the probability that you draw a third ace given that you drew an ace on the first 2 draws. Well, we can figure this out by saying, since we've already drawn 2 aces, there are only 2 left in the deck. There are 2 possible ways to draw an ace. And how many possible outcomes are left? There are only 50 possible outcomes because we already drew 2 of the cards out of the deck. So our final answer for the probability of drawing 3 aces when drawing 3 times from a deck with no replacement is this right here. Next, we have Bayes' formula, also known as Bayes' rule. And this is very important in probability, as it allows us to relate the probability of A given B to the probability of B given A. The formula itself is that the probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. Now, where does this equation come from? Well, if we start with our equation that we had for the normal conditional probability, the probability of A given B is the probability of A and B divided by the probability of B. If we use the multiplication rule on the probability of A and B right here, we know that the probability of A and B is the probability of A times the probability of B given A. That's from the multiplication rule. And then if we do a little flip-flop between these 2 terms right here, using the commutative property, we get the probability of A and B is the probability of B given A times the probability of A. And finally, if we just plug that back in right here, that gives us probability of A given B is the probability of B given A times the probability of A divided by the probability of B. This is a pretty challenging topic, so let's try a practice problem. Let's say you're in a job interview and your job interviewer has a lie detector. The lie detector will either read true or false. Now let's say if someone is lying, the test says they're lying 90% of the time. If someone is telling the truth, the test says they are truthful 85% of the time. And finally, we know that only 5% of people lie. The question we are being asked is, if the test says you are lying, what's the probability that you are telling the truth? So this is actually a pretty difficult question, but it forms the foundation of all types of Bayes' rules problems. So I'll walk you through step by step and we'll go pretty slow. Well, the first thing we do, like always, is to define our events. So let's say L is the event that someone is lying. And let's say L star is the event that the detector reads lying. Now let's do the same thing and define our events for the truth telling. So let's say capital T is you're telling the truth, and let's say T star is that the detector reads truth. Now that we have our 4 events, let's figure out what we can learn from the problem statement. So from the problem statement, we know if someone is lying, the test says they're lying 90% of the time. That's the same as the probability that the detector reads lying, given that they are actually lying, equals 90%. Now the second statement, if someone is telling the truth, the test says they are truthful 85% of the time. That's the same as the probability of the detector reading truth given true equals 0.85. And since the lie detector can only read truth or lie, the complement of this, the probability that the lie detector reads truth given that they're lying, should be 0.1, which is 1 minus 0.9. And the complement of this, the probability that the lie detector reads lying even though they're telling the truth, is actually 1 minus 0.85 equals 0.15. Finally, from this statement right here, if 5% of people lie, we know the probability of L equals 0.05. That's the probability that people lie is 5%. And that also means that the probability that people tell the truth is 0.95. That's just the complement of the probability that people lie. And then to conclude, what are we actually being asked for? The question says, if the test says you are lying, what's the probability you are telling the truth? So what we're looking for is the probability that you are telling the truth given that the test says you are lying. So we're looking for this right here, and we have all these other terms that we figured out that can help us along the way. So let's calculate this using Bayes' formula. So I've consolidated all the stuff we need to know from the previous slide, and we're trying to find the probability that you're telling the truth given that the lie detector reads that you're lying. So using Bayes' formula, the probability of A given B equals the probability of B given A times the probability of A over the probability of B. So in this case, probability of T given L star is the same as probability of L star given T times probability of T over probability of L star. Okay, so right away, we know this term right here is the same as 0.15. So that's something we can just plug in. And same thing goes for the probability that you're telling the truth. That is 0.95, and we can just plug that in as well. Now the real difficulty comes in trying to figure out what is probability of L star. What's the probability that the detector says you are lying? So let's try to figure that out. What is P of L star? Well, that's just all the ways that the detector can say you are lying. What that actually ends up being is the probability that you are lying given that you're actually lying times the probability that you're lying plus the probability that it thinks you're lying even if you're telling the truth times the probability that you're telling the truth. This term right here essentially adds up all the possible ways that the lie detector can think you're lying times how likely each of those outcomes are to occur. It essentially covers all the possible ways that the detector can say you're lying. So that's how we get this probability of L star term right here. So from there, we can replace our denominator with that term we found right there. And then we have all the stuff we need, and we can just plug in some numbers to find our answer. So the probability that you're actually telling the truth, given that the lie detector says you are lying, equals probability of L star given T, 0.15, times probability of T, 0.95, divided by probability of L star given L, which is 0.9, times probability of L, which is 0.05, plus probability of L star given T, which is 0.15, times probability of T, which is 0.95. And that gives us a final answer of about 0.76. Our next topic is odds. And odds is a pretty simple topic. It might be quite intuitive if you know anything about betting or any similar type topics. The formal definition of odds are how likely is something to happen versus not happen. And that is calculated by the probability of A, the probability that the event occurs, divided by the probability that the event doesn't occur. So for example, if you say the odds are 5 to 1, that's a way to say probability that the thing happens is 5 times greater than the probability that it doesn't happen. Or if you have odds such as 0.5 to 1, it's twice as likely to not happen versus to actually happen. So let's take a look at an example. Let's say you have 5 pink balls, 3 orange balls, and 7 green balls in a box. If you draw a ball randomly from the box, what are the odds you draw either a pink ball or an orange ball? See if you can figure it out. Well, we know from our odds equation that the odds are the same as the probability of A over the probability of A complement. Now, what's the probability of A? The probability that you draw either a pink or an orange ball. Well, there are 8 options that you can draw for the orange or pink ball, and there are 15 total options. So the probability of A is 8 divided by 15. Now, what's the probability of A complement? Well, A complement is just all the ways that you don't draw a pink or an orange ball. And since there are 7 green balls and 15 total balls, that gives us 7 divided by 15 as probability of A complement. So that gives us a total odds calculation of 8 over 7. There are 8 to 7 odds that you pick a pink or orange ball. Our final topic for today is independence. And independence is kind of intuitive. It's kind of what it sounds like. Do the events depend on one another? If they don't, they're independent. The formal definition of independence is that 2 events are independent if the probability of event 1 and event 2 equals the probability of event 1 times the probability of event 2. Or you can also put it that the probability of A given B equals the probability of A, and the probability of B given A also equals the probability of B. In general, if we have a lot of events, for example, A, B, C, D, and so on, they're independent if the intersection of all these events is just all the probabilities of those events multiplied together. Now, a common question you might get asked is to check whether events are independent. So let's take a look. Here's our practice problem. If you flip 2 coins, is the first flip being heads independent of the second flip being heads? See if you can figure it out. Intuitively, the answer would be yes. Like, why would the first coin flip affect the second coin flip at all? So right off the bat, we know they're independent. But let's just try to prove that using our definitions. So let's define A as the event first flip is heads. And let's define B as the second flip is heads. What we're trying to show is that the probability of A and B equals the probability of A times the probability of B. This is what we need to show right here. So if we have our sample space of all the possible outcomes, heads heads, heads tails, tails heads, and tails tails, there's only one outcome in which event A and event B are true, in which we both get our heads on the first flip and the second flip. That's this term right here. So the probability of A and B is 1/4. 1 out of our 4 options has both flips as heads. Now we're trying to show that that's equal to the probability of A times probability of B. Now what's probability of A times probability of B? Well, that's just the probability that the first coin flip is heads, which is 1/2, and the probability that the second coin flip is heads, which is also 1/2. So if we have 1/2 times 1/2, that equals 1/4, which is exactly the same as the probability of A. Thus, we can formally prove that these 2 events are independent. Now, along a similar vein, let's try another example. If you flip 2 coins, is the first flip being heads independent of the number of heads being odd? So again, let's say A is the first flip heads, And now let's define B as the number of heads are odd. So again, we want to try to prove that the probability of AB equals probability of A times probability of B. So what's probability of A and B? What's the probability that the first flip is heads and the number of heads is odd? Well, the only case in which these are both true is this term right here. If you flip a heads first and then you get a tails after. So the probability of A given B is 1/4. And then what's the probability of A? The event you get the first flip is heads. That's again 1/2 times the probability of B, the probability that there are an odd number of heads. Well, there are two options where there are an odd number of heads. So the probability of B is 2/4. And this term equals 1/4. So again, these events are independent. Lastly, let's try one more practice problem building on what we just did with the previous two. If you flip two coins, are the first flip heads, second flip heads, and number of heads odd, all independent events? So essentially, we're combining all three of these events. Now, the question we're being asked is essentially, is the probability of A, B, and C equal to the probability of A times the probability of B times the probability of C? If we look back at our sample space, we again find that the probability of A is 1/2, that the first coin flip is heads. The probability of B, that the second coin flip is heads, is also 1/2. And the probability of C, that there are an odd number of heads total, is also 1/2. So that means this right side of the equation equals 1/8. Now the question is, does this also equal 1/8? Well, probability of A, B, and C is essentially asking, what's the probability that the first flip is a heads, the second flip is a heads, and we also have an odd number of heads? Well, if these two flips are both heads, that means we have two heads. There's no way we can have an odd number of heads. So the intersection of these three events is actually the null set. There's no possible way that this can happen. So the probability of A, B, and C is actually 0. And since 0 does not equal 1/8, these two events are not independent. So our solution to this question is no, they are not all independent. The number of heads actually depends on A and B. And with that, we've now covered all of independence, and that concludes our coverage of all of conditional probability. Please leave any questions or confusion you have down in the comments below. I'll be sure to answer. And if you learn anything, I'd really appreciate it if you subscribed. Thank you very, very much. Please look out for more videos in the future. Have a nice day.